everyone. The topic of the lecture today is names, scopes, and bindings in programming languages. So, what exactly do we mean by names? Basically, are any identifier or mnemonic character strings used to represent something in the program, instead of using low-level concepts like addresses or basically references in the code. So a name can basically represent an abstraction in a complicated program fragment, like the name of a method, that's a control abstraction, or a class, that's a data abstraction, a variable, that's also a data abstraction. The name of a module, that's in fact also a data abstraction. In some cases, in some programming languages, even symbols like plus can be a name, can also be a name. We can actually override or redefine the operators. A binding is actually when do we associate that name to the actual thing, the semantics that it names. Like for instance, in the case of a variable, when we actually associate the name with the value of that variable. In general, binding times refer to the notion of resolving any design decision in a language implementation. For instance, a static binding to a function. This function identifier basically identifies a function definition, and it's bound to that function definition at runtime. At runtime, at least in some languages like Java, we cannot actually redefine the function. So the function is bound to that definition. But in general, the binding time refers to different times, depending when the name is actually associated with its value. So for instance, we can talk about language design time, binding times, when we design what are the possible types available in our system. So basically we associate integers to int. Now, later today, we are also going to talk about names for variables, and the names for variables are important for identifying for every point in the program what actually are the variables that we can use or we can assign values to. And for any variable, we can define the scope of that variable, which is the textual region of the program in which that binding is active. And basically the scope is that set of the region of the program where we can use that binding. So for instance, if we define a variable in Java, between the point that we declare the variable and the end of the block in which that variable is declared, we can use that variable. The scope of that variable is between the point that it was defined up to the end of the method in which it was defined. In other languages, like for instance in C#, or even in Java, the global variables are available within the entire class. So the scope of the global variable is global for that class. The complete set of bindings, in effect, at any given point in the program is known as the referencing environment. So for instance, during runtime, when we execute statement by statement, the set of variables that is available, or the set of names that is available, because names could actually stand for methods that are available, classes that are available, modules that are available, that are in the user's space. That is called the referencing environment. The referencing environment is the set of all the bindings that are in effect at any given point in the program. So the binding time may mean a lot of things. It depends on what do we bind. So when that decision was taken for binding that name to the actual meaning of that name. And there are many times when such a decision about bindings are taken. For instance, at language design time, we bind the keywords, like we decide what are the control flow constructs. So if that name, or that name while or for are bound to their meaning. Basically, we decide on the fundamental construct flow constructs, the set of fundamental primitive types, like for instance int, float, and so on, the variable constructors, for creating complex types, and many other aspects of the language that are chosen when the language is designed. Then, at another time, which usually is a little bit after the design time, called the language implementation time, we decide the different precisions. At the implementation time, we decide that there are multiple integer types or whole number types, int, int, short, byte, long, and so on. So we decide on names that specify the fundamental types, the coupling of input-output to the operating system notion of files, the organization of the stack and the heap, and other binding time decisions. Then, as programmers, we choose algorithms and names for our variables. So we are actually binding a meaning for the variables that we have in our program. At compile time, the compiler plans for the data layout, the mapping of higher level constructs, like classes, let's say, to machine code, and it makes basically binding decisions. It decides where in memory are basically stored the functions that we define. So it basically binds the function name to a certain region in memory that represents that function. At linking time, we also make decisions, or the compiler makes decisions about basically where is the program in virtual memory. If we are using libraries, where are those libraries? It chooses the overall layout of modules that are used, and it binds the modules to their actual location in memory. At load time, we transform from virtual addresses to physical addresses. The processor memory management will translate all the virtual addresses, which could be actually could be taught as names, into the actual physical address for every instruction at runtime. And then basically all of these are possible binding times. What we are interested in as users, but as implementers we can be interested in any other issues of binding times. What we are interested in is when is the binding time of variables, because we are actually defining variables and we want to know when they are actually bound to values and we can use them in the program. Runtime, as we defined it before, is something very, very broad. It actually covers the span from the beginning to the end of the execution. But that includes program startup time or loading the virtual machine, entry time for every module, elaboration time when basically a first declaration is seen, procedure entry time, block entry time, statement execution time, and so on. So runtime is quite broad. In general, we have two terms. One is static, or static analysis of the program, which refers to things that were done before runtime, and dynamic, which refers to things that were done at runtime. In general, if we have later binding times associated, they are associated with greater flexibility. Like, let's take a very, very simple example. If we bind at language design time the keyword while, it's not very flexible. We cannot change in a program the meaning of while. But if we bind in our program a variable x, we have greater flexibility. We can change its name to y. We can assign a different value to it, and so on. So early binding times are associated with greater efficiency, because these are, like, for instance, keywords are implemented in the virtual machine as very optimized, while later binding times are associated with more flexibility. Compiled languages tend to have early binding times, and interpreted languages they tend to have later binding times. Basically, every statement is executed, is interpreted at one by one, so we can make decisions about binding at any point that we execute a statement. Some languages try to do both. For instance, JVM leaves part of the code, usually complex expressions, unevaluated, until it actually needs to evaluate them lazily. Just before they are needed, it will evaluate the values of these expressions, and it will do bindings when necessary. So for any keyword or for any expression, any variable or any name, we actually have a set of key events that during binding. And these are the fact that for a reference type variable, we usually create an object, then we create the reference, which are the binding of reference to variable, which is basically using binding. If we finish using that variable, we assign null to it, to that reference, then we deactivate the binding. We can actually do also that by deactivating the binding when we enter inside methods. We call a method, the bindings that we had in the parent method may be actually temporarily deactivated. And when we exit the method, we reactivate those bindings. Now again, we have the name associated to a certain value in the parent method. The moment that we assign null to a reference, we basically destroy the binding between the reference and the object could be actually also destroyed or garbage collected. So the period of time between the creation and the destruction of a binding is called name-to-object binding, and is called the binding's lifetime. If the object outlives the binding, it's called garbage. So for instance, if a variable that was pointing to an object in memory is deleted, like for instance we exit the activation record or the frame of in the stack, and that variable is deleted, the object in the heap still exists and is called garbage, and it will be garbage collected. If the binding outlives the object, if for instance we delete an object in C and we still have a reference to that object, that reference is now called dangling reference, because it actually points to nothing in memory. So if the object created, for instance, with a C++ new operator is passed as a parameter to a method, and that method deletes it with a delete function, then when we exit the subroutine and we are in the parent method, in that parent we have a reference to an object that was deleted. And that basically is bad. That's called the dangling reference. Storage allocation can be done in 3 different segments of memory. And most of you already know this. Basically, if we have code, we can store that code in the global or static segment of memory. It stores static data fields which are associated to the class itself. It stores the class itself, methods, and so on. So for all of these, we actually give absolute address that will be retained throughout the entire program execution. The first programming languages, like Fortran, only had a static segment of memory. So all the variables were declared at the beginning of the program, and everything was allocated at the beginning of the program. So then from there on, you only had one single static segment of memory, and you couldn't allocate new locations in memory during the execution of the program. The stack is used for method invocations. Basically, we allocate frames in the stack for every method invocation, and we deallocate it in a last in, first out fashion, LIFO, usually in conjunction with method calls and returns. The heap is used for allocating objects dynamically. So we can allocate and deallocate at any arbitrary time objects in memory, and they also require a complex storage mechanism to eliminate fragmentation, internal and external fragmentation. And also it requires algorithms for garbage collection, like mark and sweep algorithm, or a counter for every single object to count how many references are pointing to that object. There are also other mechanisms for garbage collection. We are going to talk about some of them, like hierarchical garbage collection, which is used in Java. Static allocation is used for code. and small constants, like for instance internal strings that are found, constants that are found during the compilation time in the program, and they are allocated on the static segment. So they store globals or static variables. They store explicit constants like strings that are found during compilation time, like print hello world. Hello world new line is actually a constant. We don't need to create it at runtime, so it takes time and space at runtime. So we can actually construct these constants in the static segment of memory. And these are also called manifest constants or compile time constants. And an example of that is internal strings. Arguments and return values in some programming languages are also stored in the static allocation. Like for instance, Fortran did not have recursion. So for every method, you can actually store the variables, the arguments of that method in the static segment of memory. So basically, as long as you don't need multiple copies of those arguments, those can be stored in the static segment of memory. Temporaries are basically intermediate values produced in complex calculations, and they can be also stored in the static segment of memory. Bookkeeping information like the return address of the current subroutine, a reference to the stack frame, and the caller of that stack of that method can also be stored in registers and in the static segment. So basically those that are needed at runtime, and there are a single copy of that value that is basically stored in a location that the program knows where to find it. Why do we need a stack segment of memory? Because we have recursive routines. Basically, we have methods that call recursively themselves with additional arguments, basically with other arguments than the ones that, the other formal parameters than the ones that were arguments or actual parameters to the method. So we need to basically allocate multiple copies for the same names and more specific copies for every single method invocation. Moreover, when we exit methods, we don't need the arguments and the local variables for those methods. So we can also reuse the space by popping out from the stack when we return from methods the activation record for those methods. Every time we call a subroutine at runtime, it actually creates a new frame or activation record for its own parameters, local variables, and return address for that specific frame. So in fact, there are a lot of information stored in these frames, and the maintenance of the stack is actually the responsibility of two methods called prologue and epilogue. Prologue is code executed when we enter a method, basically creating the frame, copying the values if we have call by value from the actual parameters to the formal parameters in the method. And epilogue, which is executed at the end, basically when we exit a method, we have to return the value from that method and also delete the frame and basically reset the program counter and reset the stack pointer to the top of the current top of the stack. These subroutines are called the calling sequence, are basically code executed by the caller immediately before and after the call. There are two pointers that are important and two registers that are actually important for stack execution. The frame pointer, which points to a known location within the current frame. It usually points above the parameters for the current method. It points to the parameters above the return address for the current call. And the start pointer, because above that frame pointer, which is basically a pointer to the current parameters and the return address, we have a pointer that points to the top of the stack, because we can have local variables. So The first last used location on the stack is pointed by the stack pointer. The stack pointer will basically point to where the arguments for the next call, if we are actually making a next call, would point to, and we can get with fixed offsets the local variables from that stack pointer and the parameters from the frame pointer. And this is an example. Let's assume that we had some code and the main program calls the procedure A, the procedure A calls the procedure B. The procedure B can call recursively itself, or it could be calling the procedure C, which calls the procedure D and E. And we are currently executing here. We are basically in the procedure C during the execution of the procedure D. So the stack pointer points to the first free block on the stack. The frame pointer points to the parameters of the procedure D. The procedure D was called from the procedure C, which was called from the procedure B, which was called from the procedure B, which was called from the procedure A, the main method. The stack usually grows up, so the next frame that will be allocated, let's say, after we deallocate D, we would execute E, and the frame will be allocated on the top of the stack. The subroutine, as I said, contains the return address, the frame pointer, possible basically parameters and miscellaneous bookkeeping, local variables, temporaries, and arguments to any call routine. So in fact, it will call the next routine, and it will also store the arguments on the stack, some programming languages. And this is an example that I usually include in my CSE307 class. Basically, it's a main method which invokes a max method. So if we execute it on the stack, this is what happens. We first create an activation record or a frame for the main method. The main method defines the variable I, defines the variable j. It basically allocates space for it on top of the stack. It always, when you read the variables are in the reverse order as we store them on the top of the stack. Then it defines the variable k, declares it, and it invokes the method m. And the method m needs a new frame on the stack. So in this case, it creates a new frame that contains the formal parameters num1 and num2, which check the values of the arguments I and j. And in Java, we have call by value. We actually copy I into num1 and j into num2. And then we start execution of the max method. Since we declare result, and since number 1 is greater than number 2, 5 is greater than 2, the result is assigned 5, and we return the result. In which case, the epilogue deletes the current frame of the method max and continues with the current method main to print out the result 5. So as I said, the maintenance of the stack is done by these two subroutines, prologue and epilogue, and we can actually do optimizations. And usually space is saved by putting as much in the prologue as possible. If it's possible and the methods are not recursive, we can even unfold. Basically means execute the method that we call on the current frame. Space is saved by basically putting as much stuff in the caller instead of putting it in the called method, or combining what is in both places. That's basically unfolding, or basically executing in the current frame also the method that we invoke. One cannot return references to objects on the stack, because that would basically be the moment that we return from the stack from the method, that those objects will be deleted from the stack. Now, one thing that many of these optimizations would do, instead of actually storing the parameters on the stack, they would use registers. For instance, for the latest architectures, instead of actually storing parameters, if the number of parameters is less than 5, it actually would store them in special registers in main memory instead of actually storing them on the stack. The next type of allocation is heap-based allocation. Heap is for dynamic allocation. It basically, at arbitrary times, we can allocate space on the heap, extend the space on the heap of known objects, and actually delete them at any time. A heap is a region of storage in which we can actually allocate and deallocate subblocks at any arbitrary time. And dynamically allocated pieces of data structures could be objects, strings, lists, sets, whose size may also change as the result of adding additional elements. But they may have fragmentation. So there are two types of fragmentation. When we are actually storing in a block that is larger than the required object that we need to store, and external fragmentation. The easiest example of internal fragmentation is storing of Boolean values. For Boolean values, we only need 1 bit, but 1 bit is not addressable in memory. The address is basically address bytes or address locations or blocks of memory of 32 bits or 64 bits. We cannot address a single bit. So if we are allocating space, even if we allocate 1 byte to store a Boolean, we are only using 1 bit. The other 7 bits are unused. That is called internal fragmentation. Basically, based on how much space we have allocated, we can actually we have some space that is completely unused. External fragmentation is when, because of the fact that we allocate and deallocate objects at any arbitrary times, we can have a lot of holes in our memory. Basically, in the heap, we may have the gray areas used and the white areas unused. And at some point, we would have an allocation request for an object for which we cannot actually find any single place in memory to put that object. And the reason why is that we cannot find a region large enough to satisfy the request. However, the unused space would actually, if we compose it and we would reallocate the objects on the stack, we have enough free space to allocate that new object. So how can we avoid fragmentation? We can actually use storage management algorithms. We actually can keep a list of all of the free blocks in memory, and we could use algorithms like first fit and best fit. First fit will select the first block in that list that is large enough to satisfy the request. Best fit would be searching for the entire list to find the smallest block that is large enough to satisfy that request. Because if it's smallest block, then we have the least fragmentation possible. In addition to that, we can also allocate blocks in some order, like we would adjust the pool based on the need of how much space we actually need. So a first fit will be actually matching a best fit system. The body system would actually keep the blocks in standard sizes as powers of 2. So we have blocks of size of 4 bytes, 8 bytes, 16 bytes, 62 bytes, and so on. The Fibonacci heap would keep the standard size blocks as Fibonacci numbers. So we basically have 1, 1, 2, 3, 5, 8, and so on sizes of blocks. Another algorithm to actually avoid fragmentation is compacting the heap. Compactation will actually move already allocated blocks to free larger blocks of space in memory. Moreover, we may have garbage in memory, like for instance objects that are in the heap that are not referenced currently by any variables. So in languages where the allocation is not explicit, basically manual deallocation can be done in C or C++ with dealloc in C and delete in C++. But in languages where you can't do that, manual deallocation, you need to rely on some algorithm to do garbage collection implicitly. In fact, in languages that allow deallocation, manual deallocation, errors concerning manual deallocation are most common type of errors. Like for instance, you have memory leaks in languages like C. That is, memory leaks means that methods that used and created objects did not delete those objects after they returned. So objects are implicitly deallocated in garbage collection when they are no longer referenced. And that is usually costly because you basically take time to find which objects are the ones that are not used anymore, not referenced anymore. But the algorithms that are implemented are basically quite powerful. First, the first type of algorithms is called reference counting. Reference counting is keep a number of how many references point to every single object. However, as we will see in a simple example, are not always successful. Because if you have circular lists, even if there is no more reference to that list, every single element in the circular list has a reference to itself from one of the other preceding elements in the circular list. Mark and sweep is an algorithm that fixes that issue. Basically marks all the nodes with not used, then it follows the variables in the stack to actually mark the ones that are used recursively in memory, and then the ones that are not used at the end of marking everything will be deleted. Again, it's very costly because we have to do this algorithm, which is a quite complex algorithm, to delete objects that are not used from memory. Finally, there are more complex schemes like copying and generational or hierarchical garbage collection, which basically keeps different objects in different or basically different sets of variables or different locations in memory. So young variables which are deleted often are basically kept in a region where we actually do a lot of garbage collection, while old variables that were created for the entire execution, for instance, are deleted more seldom. Now there are also algorithms for garbage collection which basically are ran either in parallel with the current execution, like for instance concurrent algorithms for garbage collection or incremental algorithms for garbage collection, which when we delete an object or a variable, only those objects that are referenced by that variable are incremented or deleted if necessary. Or there are algorithms that stop the execution of the current program to do garbage collection, and then they return to the current program and restart it. Those are stop-the-world garbage collection algorithms. As I said, later this semester, when we talk about execution of methods and execution of programs, we are actually going to talk in detail about mark and sweep garbage collection. Okay, so next we'll continue with scoping rules. So the binding scope is the textual region of the program in which binding or a variable is active. A scope in a program is that maximum size of code in which no bindings change for a given variable, and in which in some languages you are not permitted to redeclare that variable. The scope of the binding can be determined statically or dynamically. Basically, we have scoping rules, and one scoping rule could be that in order for a variable to be used, and this can be done statically, it must be declared first. It must be declared before we use it. So, in fact, there are different scoping rules even for this definition, because in Java, local variables must be declared and initialized before we can use them. That's one scoping rule. Another scoping rule says that class properties like static values and methods are available even if they are declared or defined after the current piece of the code in the class. So there are different scoping rules for different variables. Local variables are available between the point that they are defined up to the end of the block. global variables or static variables and methods are available within the entire class. Those are two examples of scoping rules. Basically, they define what's the scope of that variable, what is the region of the program in which that variable is active, or that method name is active. Another scoping rule. Can we actually define a variable in the global segment or the global block and then redefine it in a local method? Do they refer to the same binding or not? And it depends again on the language. In Java, if you would define the variable as a global variable and then you would define a variable or assign a value to a variable inside a method, it may actually mean the same variable, or it may mean if we declare the variable inside the method that the outer variable is actually hidden by the local variable with the same name. In Python, you have to declare global. Basically, you have a scoping rule that defines that unless you define explicitly that you are using the outer variable, you are actually redefining an inner variable. So in static globing rules, the bindings are defined by the physical lexical structure of the program. So static scoping, also called lexical scoping, are rules that basically define within the syntax of the program where are variables or names available. So for instance, in the old BASIC and Fortran, because you only had one segment of memory, which was the static segment of memory, you had one big scope. All the variables are available from the beginning of the program where were defined in the entire program. No matter that you were in a method or you were in the main method. Now, for instance, Java has the scope of a function. Variables live throughout the function execution or throughout the point that they were declared up to the end of the function. Then you have blocks. If you can define a variable within a block. A variable within a block is again available until the block finishes. Then you have nested subroutines. If you define a variable in an outer block, it's also available within the inner block. Those are static scoping rules. If a variable is active in more scopes, then the closest nested scope is the one in which the rule applies. Like for instance, in the previous example, the inner local variable overrides the outer local variables. Inside the function f, the inner a is assigned to b. So lexical scoping rules were used initially in Algol, and then they have been picked up by many other languages since then, like Pascal, C, Java, C#, and so on. In most languages with subroutines, we open a new scope every time we enter a subroutine. We create bindings for local variables. We deactivate the bindings for the global variables or the variables in the main method. In the parent method, we deactivate the global variables that are redeclared. These variables are said to have a hole in their scope because they are not available within those methods that redeclare the variables. And we make the references to reference parameters. When we exit the subroutine, we destroy the bindings for local variables and we reactivate the global variables that were deactivated. This process is called elaboration. Basically, it creates the bindings for entering the subroutine. We allocate space for storage, and we even propagate exceptions as the result of elaboration of declarations. So with static scoping rules like C, Java, Python, a scope is defined in the lexical structure of the program, and we determine for every variable what are the variables available in every part of the program. Basically, we typically choose the most recent active binding at compile time, and we basically exit, when we exit a method, we undo the bindings. Again, one of the most common static scoping rules is the nested blocks. The fact that the most closely nested rule identifier is the one that is actually currently in the referencing environment. The original identifiers, which are defined in the global segment, are hidden by the current definition. And this is also used, basically the same definitions for scoping, static scoping rules are useful for classes in object-oriented languages. So let's see an example. We define the procedure P1. The procedure P1 uses the formal parameter A1 and the local variable x. In Pascal, you can define procedures within procedures. If you think about Java, you can think that P1 is a class and P2 is a method within P1, maybe an inner class. So you can have also a method within that inner class. P2 has a parameter A2 and has a method, a procedure P3. P3 has a body. For instance, at this level, we can find what variables are available for invoking and what names are available. Like you can invoke recursively methods, which are at the same level, basically, which are known to this body. So in the body of P3, we can invoke, we have access to P1, we have access to the argument A1, we have access to the global variable x, we have access to P2, we can call it recursively. We can use A2, the argument of or data field of P2. We can call recursively P3 in the body of P3. That would be a recursive method. We can use the argument A3. We can also call the procedure P4 because that is an outer procedure. It's like another method in the current class or in the outer class. But we don't have the access to the data field A4 because that is called, so it's passed as a parameter when we invoke P4. So at every level we can compute what is called the referencing environment, the set of all the names that are known at that position in the program. And we can do that just because we have static scoping. Because dynamic scoping, as we will see, involves the stack. You have to know what was called before the current method, and what was called before that, and before that, and before that, and so on. So static scoping is when we actually seeing a program, we can identify what's the set of variables available in the program at that point. Now for every variable, we can create the scope of the binding of that variable. So A1 is available in the entire program, but X is only available in P1, is not available inside the function F1. Because in the function F1, we define a variable x that has the same name in the entire function. So we say that x has a hole, which is basically inside the function F1. When we have an expression about x, that x means the local variable x, not the global variable x. So here we actually have, for every single variable in the program, the scope of that variable. Basically, where is that variable available in the program? A1 is available in the whole program. We talked about x. P2 being a method is available to be actually invoked in the entire procedure P1. A2 is available only within the procedure P2. P3 is available only within the procedure P3, only in the inner class. It's like a private method for that class in Java for the procedure P2, and so on. We see that the local variable x is actually different than the global variable x. So that global variable has a hole because we have a local variable available at that location. As I said, at every point in the program, you can find what is the set of names known at that point in the program. That is the referencing environment of that line, of that position. So how is static scoping actually implemented? Actually, the easiest way to implement static scoping is not to actually look at the original program, because that would require some kind of parsing during runtime, but actually by keeping static links in the stack, which points to the parent frame. So for every method, you need to know in which frame that method was declared. So basically, let's say for P3, we have a static link to P2, the latest frame for P2. In P2, we have a static frame to P1, the latest frame for P1. So if the subroutine is declared at the outermost nesting level, then it will have a null static link, but otherwise, basically it has a static chain. It points to its parent in the code, then which points to its parent in the code, which points to its parent in the code, and so on. And the length of that is k levels deep. Basically, we have a set of links that identify that if we don't find the variable in the current frame, we may find it in the parent frame. If you don't find it there, we may find it in the parent frame, and so on. So for instance, inside the function f1 here, I want to use a1. Since the function f1 does not define a1, I'm looking at p4. p4 doesn't define it, so I'm looking at p1, which defines it. So I have these links between f1 has a link to p4, p4 has a link to p1. And here I have an example. For instance, the current method that is executed is C. And C is defined within the method B, which is defined within the method A. So let's say that I need a variable x. X is not defined in C. I'm looking through the static link if it's defined in B. If it's defined in B, then I use it. If it's not defined in B, I look if it's defined in A, and so on. So this is during runtime, I have to maintain the static links, and I follow the static links, or we follow the static links to find variables that are used in the program. So there are many different static scoping rules. For instance, declaration order is a rule that a name should be declared before it's actually used in the program. In some languages, even in modern languages, a variable, if it's declared, is available in the entire block, or the whole block of the program. So for instance, in C#, defining a variable in a block makes every external declaration of that variable hidden. So for instance, even if only we declare n equal with 20 here, m is equal with x will actually, this is equal with n will be the local n, which is not declared yet, but it will be declared later, instead of the global n. Next is dynamic scoping rules. So dynamic scoping rules are actually the original scoping rules. Before we had static scoping rules that we are used to. The original programming languages were using dynamic scoping rules. So a lot of bash scripting languages, or Perl, also functional programming languages are using dynamic scoping rules, which basically are dependent on the current stack, on the calling sequence. Basically they look down in the stack to find every single name. If it's not in the current frame, it would go to the next frame in the stack. And if it's not there, in the next frame in the stack, and so on. So for every reference, we use the most recent active binding at runtime. So let's actually see an example. Here is a very simple example. We have a global variable total assigned 0 that is in the main program. In the main program, we also have some methods, like the method add that adds total with 1, and the method myfunc that defines a new total variable equal with 0 and invokes add. And we invoke in the main method add. So if we call add from the main method, originally the main method total was 0. Add will actually, since it does not have the variable total, it uses statically, or basically uses dynamic scoping, looks down in the stack to find the first variable total in the stack, and increments total with 1. We finish the method add, we pop it out from the stack, and we call the method myfunc. Myfunc defines a total that is equal with 0, and calls add again. Add will look down in the stack and will increment the total from myfunc with 1. So when add finishes, myfunc finishes, and the main method finishes, we print the total, which is 1. The global total, that is 1. And you can already see that if we would have run this in a static scoping system, then we would have added twice the global variable total with 1. So the value that would be printed would be 2, not 1. So in dynamic scoping, this would print 1, and in fact each one of the totals is incremented with 1. And we have 2 of the states of the stack in this case. Any questions? So the rule is that at any point, all that we do, we look down in the stack. It's always look down in the stack, because it's always about what is the first object that is seen, or the first variable that is seen down in the stack. Any questions? Okay, great. In fact, given the fact that we only determine at runtime what is the value of variables, even the user input and the sequence in which methods are invocated actually make decisions about which variable is the one that is currently used in the program. Okay? So for instance, in this program, the user is asked to enter an integer. If the user enters a positive value, it calls second. If the user enters a negative value, it calls first. Second defines a new variable a and then invokes first. And if we follow the path that we basically read a positive integer, then the value that is assigned, or the variable that is assigned a equal with 1 is the variable in second. While if we enter the negative number and we called first, the value that is equal with 1 is the value in the global segment of memory, or the scopes program, instead of the variable in second. So we would write, for instance, 0 if the user enters a negative value, and we would write 1 if the user enters a positive value in the main method. In static scoping, it will always print 1, the global A. In dynamic scoping, if let's say we read a positive value, then it prints a 2. If we read a negative value, it prints a 1. And it prints 2 because the global A was equal with 2 at this line. So not 0. That was my mistake earlier. Any questions? Okay. So dynamic binding, as we defined it now, is very shallow. It just looks down in the stack. But that doesn't take into consideration the referencing environment. Sometimes, like in certain programming languages, we actually assign to function variables also a function with its referencing environment. This is called closure. We actually pack the function together with its referencing environment. Now, we'll see examples of deep binding rules, basically deep scoping, deep binding rules, dynamic scoping with deep binding a little bit later today. But first, what exactly were languages that use dynamic scoping rules? Most of the original languages like Lisp, Perl, some of the newer languages like Ruby, C#, Shell, Bash languages like PowerShell and Bash are using dynamic scoping. Such languages in many cases do not have type checking at compile time because many of them are interpreters, but others, they don't actually know the type, and they don't can actually do typing at static time because the type of values is only known at runtime when we actually have the stack. A common feature of dynamic scoping rules is actually to provide implicit parameters, because if you don't give parameters to a subroutine, it just looks down in the stack. So it will take those parameters within codes from the frames of the parent methods to the current method on the top of the stack. There are alternative mechanisms, like for instance, parameters could take default values, or there are optional parameters in certain languages. So now, talking about the different types of binding, first we have to define the referencing environment. So all the variables or bindings active at any given time during execution is what is called a referencing environment. So when we take a reference to a function in deep binding or in dynamic scoping programming languages, we can actually decide if we want to pass just the name to that reference of the function, or also we want to pass the referencing environment. And in fact, there are two types of binding: deep binding and shallow binding. Deep binding binds the environment at the time that the procedure is passed as an argument, and shallow binding binds the environment at the time that the procedure is actually called. So it's just shallow look down in the stack. And here we have an example. So this is a little bit more complex example, and please follow up closely as I basically present it. I will actually compare the outputs that will be printed in static, dynamic shallow, and dynamic deep binding programming languages. So we'll start with static. So the main method for this program defines a global variable total equal with 0, defines a method A that increments the total with 1, defines a method B that defines a variable total equal with 0 and calls the function f that we get as a parameter. It prints B followed by the total after exiting the function f. We define the function C, assign the total. We call B with A as a parameter, and we print C followed by the total. And now in the main method we invoke C, and we print the total when we exit C. So let's see what happens in static scoping. So in static scoping, we call the procedure C. The procedure C defines the variable total. It invokes the method B with A as the function f. B also defines the total, and it invokes the method f. The method f is A, so it calls the method A, and the method A increments the total with 1. The question is which total? The global total, because using static binding, static scoping, since the variable total is not defined here, is defined in its enclosing scope. So it uses the total in the main method to increment it with 1. When we finish that method A, we print the total in the method B, which is still 0. When we finish B of A, we print C followed by, again, total, which is the local variable total of C, which was never incremented, is still 0. And finally, we return to the main method, we finish the procedure C, and we print T followed by the global total, which was incremented to 1. So this is, we are used to it. Basically, it's what Java does. Now let's go to dynamic shallow. Dynamic shallow just looks down in the stack. So when we call total, it calls B of A. When we call B of A, it calls F, and it increments total with 1. So A will basically look down in the stack, and since A doesn't have total, but it was called by B, it will take the total in B and increment it with 1. So when we exit from F, which was A, and we print B followed by total, it prints B 1. Then we return to C, we print C 0, and we return to the main method, and it prints B 0. Now let's see what happens in dynamic deep. So this is the most complicated out of the three. So we invoke the procedure C. The procedure C invokes B of A, but it passes not only B of A, but it also passes the referencing environment as a parameter, the parameter f. So it basically passes the fact that at this point, if we would invoke A, the total in the procedure C would be the most specific. So the referencing environment knows the total in the procedure C. So when we invoke A from the method B, it increments the total in C with 1. Okay? So when we return in the method B after we executed A, it prints B 0. When we return in C, it prints C 1. And when we return in the main method, it prints D 0. And that's the output that we have here. Okay. We are going to do a few more examples in a few minutes. I will upload a file with a lot of examples in Blackboard after the class today. So let's see another example. Again, we are going to execute it in static scoping, dynamic scoping with shallow binding, and dynamic scoping with deep binding. So again, first we execute this in static scoping. In this program, we define x, an integer of the type the equal with 1, y, an integer equal with 2. We define a procedure add that does not declare x and y, so it just adds x plus y and assigns it to x. A procedure second that takes a procedure p as a parameter and defines a variable x equal with 2, a new variable x equal with 2, and invokes the procedure p. And the procedure first, which defines y as an integer equal with 3 and calls the procedure second with add. And we invoke first. So in static scoping, first will declare y, will call second will call p, which is add, and add will increment x plus y and assign it to x. So the global x and y, because those are the outer block of the method a, that a does not have x and y defined, the global x and y are added, and x is assigned the value 3. Then we return to the method second, we return to the method first, and we return to the main method, which prints 3. Let's see what happens in shallow binding. In shallow binding, we basically have a stack. So the method first defines the variable y, the method second defines the variable x, and when we add x with y, it looks down in the stack and it adds 2 plus 3 is 5 and assigns it to the local variable of the parent of add, which is basically second. So this x is assigned 5, we finish add, we finish second, we finish first, we return to the main method and we print the original value of x, which was 1. Now what happens with deep binding? In deep binding, we call first, which calls second of add, but also the referencing environment. So at this point, we know the local variable y, which was 3, and the global variable x, which was 1. So when we call second and second calls add will actually add the basically x that was the global x2 with the local variable where add was invoked, and it carries the referencing environment, which is 3. So 1 plus 3 is 4, and the program will print 4 when we exit all of these methods. What I advise is that you build the stacks for every one of the three cases. Basically, for static scoping, we would have a stack in which the bottom of the stack is basically the outer block for the method add. Therefore, there is a static link from method add to the main method, and it uses x and y. Then you can draw the stack for the shallow binding, which just looks down in the stack and chooses as the most important the frame right below the add. So it adds x from second with y from first to get 5, and assigns it to x from second. And finally, but when it returns to the main method, it prints the original x, which was 1. And finally, dynamic scoping with deep binding, you also pass the referencing environment. So the referencing environment, when we invoke second of add, is also part of the add function. Okay. So how is that actually implemented? Dynamic binding. It's implemented what is called closure. That the moment that we create bindings, or basically implementation of binding, we also collect the reference of that binding. So what does it mean is that when we invoke a function, like for instance we return a, but a is defined in the current foo, we also keep around during runtime the references in that stack frame, although it was basically executed already. So f is equal with foo. Foo returns bar. Bar is a function, so it comes with the referencing environment, which is a. Then we invoke bar, which is the function that we return, f that we return from foo, and bar returns the value of a. So it basically carries the referencing environment and also solves it and returns the value. So how can we implement such referencing environments, especially dynamic scoping referencing environments? In the case of shallow binding, it's easy. Basically, we have a stack of all the active variables. When we need for a variable, we actually look down from the top of the stack and we hunt down for that variable. The equivalent is actually to search the activation records in a dynamic chain. The second way is to keep a central symbol table. So basically we use small stacks for every variable that was defined as variables in the symbol table. So always we have the top of the stack of for every variable the most relevant value for that variable for the current method. Names could actually mean different things, and if you did object-oriented programming, you will see that, for instance, in Java you have two concepts called overloading, where the same name will mean multiple meanings. Basically, we overload the name for different parameters. Like for instance, if you consider languages in which operators like plus are considered names, integer addition and real addition and string concatenation are all represented by the name plus. So we are overloading the name plus with different meanings depending on the input parameters. Read and write are also overloaded when we read with the same read instruction integers or other types of parameters. And function return as a function, when we have function return implemented as a function, is also overloaded. You return the type of the argument that you actually pass as a parameter. Some languages do overloading in big time, like for instance in Java, the plus operator is overloaded about a dozen times in the language. For every single primitive type, you can actually overload it for objects and so on, like strings. However, you have to be careful when you overload symbols. Like for instance, in this program, because of the fact that we invoke max with two integers, we match the invocation with two different methods in an equal way. A method max that takes a number integer and a double, and the method max that takes a double and an integer. If we wouldn't have the invocation, we don't have an error. We overloaded correctly the method max. One that will take as the first parameter int, and the other one that will take as the first parameter double. But if we have this invocation, we will have an error in that line of code telling us that we cannot determine, the system cannot determine what is the basically method that needs to be called. We also have to make distinction between overloading and overriding, basically polymorphic functions in object-oriented programming. Like we talked about overloading when two different things are meant by the same name, but we can make the distinction based on the input parameters. But there is also overriding where the input parameters may actually be the same. So for instance, we have two at runtime to determine in a dynamic way what is the most specific definition of the function for the current object. And if an object is instance of a class, let's say Cn, and Cn is a subclass of Cn minus 1, and so on, up to the root class C0, like the class object in Java. If we invoke a method for the current object, it tries to find the definition for that method from Cn up to C0 in this order. The first occurrence of a method with that signature will be the one that will be executed. And here we have an example, which I usually use in computer science 1. We invoke the method m in Java with a graduate student, a person, and an object. We actually pass to this method m each one of these objects, and through polymorphism, an object of a subtype can be used whenever the supertype is required. Like for instance, a graduate student, a person, and an object are all objects. Then we invoke the method toString dynamically for the object x. So for each one of those objects, we have to find the most specific definition for toString. So for the graduate student does not have a method toString, but it extends the class student. The class student has a method toString. So at runtime, the Java virtual machine determines that this is the most specific method and prints student. So this is dynamic binding as I explained it a couple of seconds ago. A little bit different. Basically, the object is the instance of C1. C1 is a subclass of C2 up to Cn. And if we invoke a method p, the JVM will search for the most specific implementation of the method p in the classes C1 to Cn in that order until it's found, and then it stops the search. And this is what is the output of that program. So we have two processes going on in parallel. Method matching, which basically finds in Java, according to the parameter number and type, the method that corresponds to that specific invocation. And dynamically, at runtime, it finds the most specific implementation for the type of object for which we are invoking the method, and that is dynamic binding as we defined it before. Okay, also related to scopes is aliasing. So what exactly is aliasing? Yeah, we even have aliasing in Java when we assign a reference type variable to another reference type variable. Basically, we have two names pointing to the same object. There are issues, basically side effects. It makes the program harder to understand. The fact that when we change the value or the data field of one object through one variable, it also changes that value for another variable. But they are good for a lot of issues, like data structures, like linked data structures. An example of aliasing is when we pass a variable by reference to a subroutine, which also can access that variable directly. So we basically have two references in the same method for the same location in memory. Modules are also names. What are modules used for? They are used for actually splitting the user space into different areas. So we can actually define different meanings for our names. We can have, let's say, an average in one with the same, let's say, arrays of integers in one class, and another method or another one. We can define one class with the same name in one module, and the same and a class with the same name in another module. And finally, macros. So macros are actually just pieces of code which are substituted when we invoke the macro. The benefits of using macros are the fact that we have shorter code. We don't actually allocate space on the stack. We actually materialize or unfold the definition of the macro in the place where it's used. There are problems with macros, like for instance multiple side effects. If we invoke a macro with A++ and B++, depending if whichever is bigger, one of them, X or Y, will be incremented twice. Another possibility, another issue with macros is that we use in the macro the same variables that are used in the method that uses those macros. So in that case, we can actually have issues. Like for instance, those variables can be can have side effects. We will actually talk a little bit more about a few issues with dynamic scoping versus static scoping and the two different types of bindings in a set of examples that we will have separately in a couple of seconds. So let's see if there are any questions in the chat, and then we are going to save the recording for later for students that will join us. And we are going to talk about the homework issues, and that's all for today.